So where I left off in our last lecture was I said I wanted to calculate what the gamma function would be for 1/2. So in that case, it would just be the integral of t to the 1/2 minus 1 times e to the minus t dt. Now, in previous lectures, I used the x as the variable in the integral. Now I'm switching to t. That's just because in a minute we're going to do a change of variables and do a bunch of substitutions. So let's just start with t. But in the end, it's just that's just a variable in the integral. So if we continue on, then what we have is the integral of t to the minus 1/2 e to the minus t dt. And that gives us the integral of 1 over the square root of t e to the minus t dt. Okay, so now the question is, how are we going to solve this integral? Well, let's do a substitution. Let t equal y squared. So dt is equal to 2y dy. And if that's true, then our integral becomes 1 over y, so the square root of y squared is just y, e to the minus y squared, 2y dy. So that's kind of interesting because now the y's cancel, and I'm left with the integral of 2 e to the minus y squared dy. Okay, so now let's try and figure out what about this y squared? Or how are we going to solve this integral where we've got an e to the minus y squared? Well, the interesting thing is that, again, these variables are just kind of like dummy variables. I can choose y, I can choose x, I can choose t. None of them really have any specific physical meaning, at least. So why don't we write down our gamma function of 1/2 as the integral 2 times 0 to infinity of e to the minus x squared dx. Okay, that would be the same thing, but if we multiply those two together, if I get gamma 1/2 squared, that would give me 4, the integral of 0 to infinity e to the minus x squared times e to the minus y squared dx dy. Okay, so now I've got 4. I've got this double integral now, e to the minus x squared plus y squared dx dy. So that's kind of interesting because x squared plus y squared is basically equal to r squared if we change it over into polar coordinates. So if we change it over into polar coordinates, we get 4, 0 to pi over 2, 0 to infinity, e to the minus r squared, r dr d theta. So what we're doing essentially is integrating now over a circle in the first quadrant, where now this is r and this is theta. Okay, so that looks like it's a little bit more doable. So we've got the gamma of 1/2 quantity squared, which is now equal to, I can integrate over theta pretty easily, so that's pi over 2 times 4, and I'm left with now the integral of 0 to infinity r e to the minus r squared dr. Okay, so let's do another substitution. Let's let u equal to r squared, so then we would have du is equal to 2r dr. And so now we have 2 pi times 1/2 from the substitution integral of 0 to infinity e to the minus u du. Now that's an integral we've seen before, and that's an integral that we can solve in our sleep. And so we would get pi, the integral of this is minus e minus u, evaluated from 0 to infinity, which we've done a couple times before. So that would be minus e to the minus infinity plus e to the 0. E to the minus infinity is just 1 over e to the infinity, which is essentially 1 over infinity or 0. So in the end, we're left with is we get pi. Pretty simple answer. Amazing that we took the route that we did to get it, but what we're left with is gamma function of 1/2 quantity squared is equal to pi. So that means that gamma 1/2 is equal to the square root of pi. And so that one you should hold on to. That one try and remember, because gamma 1/2 is a good base to which build up and find gamma 3/2, gamma 7/2, gamma 15/2. We can build our way up with our recursion relationships with the gamma function. Also, it's a pretty simple one to remember. It's just the square root of pi. Now, the interesting thing is there's another important formula which I'm not going to necessarily derive, but what it says is gamma of p times gamma of 1 minus p is equal to pi over the sine of pi times p. Okay. So we could test this out with our 1/2. So if we let p equal to 1/2, then we would have gamma 1/2 times gamma 1 minus 1/2. And that's basically equal to gamma 1/2 times gamma another 1/2. So that's our gamma 1/2 quantity squared. And so that's equal to pi over the sine of pi over 2. Sine of pi over 2 is equal to 1. So that's equal to pi. So the square of the gamma of 1/2, again, is equal to pi. So we've kind of come about it in two different ways. One which we derived, the other one which I just stated as a fact, given this equation. But in the end, what we find is that gamma of 1/2 is equal to the square root of pi. Okay. So that's pretty unique. That one we should hold on to, because it'll show up later on in other derivations. Not one, because we'll want to figure out what the gamma of 1/2 is. If we think about it, we could now try and figure out what the factorial of 1/2, if you kind of want to think of it that way. But we said that we had this relationship that gamma of n plus 1 was equal to n factorial. I'm just checking my notes. Yep, that's true. So now, if I put in gamma of, say, minus 1/2 plus 1, then I would get gamma of 1/2. And that's kind of saying that taking the factorial of negative 1/2, which is now essentially the square root of pi. Now, most people don't write the factorial of a negative number. Usually we just say, at this point, you know, I'm not going to get a negative factorial. Instead, we're just going to be using the gamma function. So the gamma function now has become kind of, it supersedes the factorial. But, you know, if for some reason you ended up with what is the negative 1/2 factorial, well, you can use the relationship with the gamma function to give us that answer, which just happens to be the square root of pi.